Hello everyone, welcome to this lecture of the course heat transfer. So this is the continuation of the module radiation. So in the last lecture we have discussed regarding the shape factor and the shape factor algebra. Then we have seen the reciprocity theorem or reciprocity relation, and based on those different shape factor algebra or different features of the shape factor we have discussed some numericals. So this reciprocity relation, it is actually the radiation heat exchange between the black bodies. Okay, so that thing we have discussed in the last lecture. So today we will be discussing the radiation heat exchange between non-black bodies. What are the different equations for different type of objects? So all these things we will discuss today. Okay, so let us start this lecture. So the heat exchange between non-black bodies, this is the thing that we will discuss today. So the black body concept, it is an idealization which serves as a standard for the performance of a real body. So what is this black body concept? That thing is already discussed. When the absorptivity, this is basically one, that is everything is absorbed by a body, that is known as the black body. So there is no reflectivity or transmissivity in case of a black body. Now, in case of an engineering application, most of the surfaces are encountered do not have like black bodies which absorb the entire incident radiation or irradiation. Now, the real surfaces which are actually non-black, they do not absorb the whole of the irradiation, because and a part of that irradiation, it is reflected back to the radiating surface, and this back and forth reflections between the surfaces may go on several times, which can be seen in the below diagram. Now, as the emissivities and absorptivities are not uniform in all directions and for all wavelengths, so to simplify the problems to some extent by considering the bodies to be gray, for which the emissivities and absorptivities are constant over the whole wavelength spectrum. So this is the thing that we take into consideration in case of the heat exchange between non-black bodies. So these are applicable for real surfaces which are non-black bodies, and we consider the bodies to be gray, for which the emissivities and absorptivities, these are constant over the whole wavelength spectrum. Now in this diagram, below diagram, you can see that the heat exchange between the two different non-black parallel surfaces. So here we have considered two different parallel surfaces. One is plane 1, that is in the left side of this diagram, and another is the plane 2, that is in the right side of this diagram. Now for the plane 1, we have considered these properties, that is absorptivity, emissivity, and the temperature. These are as alpha 1, epsilon 1, and T1. And for the plane 2, we have considered those same similar properties, that is alpha 2, epsilon 2, and T2. So if the first emissive power from the plane 1 to plane 2, if this is epsilon 1, then when that emission, it will be reflected from the plane 2, it will be that fraction of that emission or the emissive power. So in that case it will be alpha 2 multiplied by E1, because some part will be absorbed. So similarly, the later emitted radiant heat exchange we can represent in this mathematical representation. So the first thing that we will discuss, it is the for infinite parallel planes, the radiant heat exchange for the infinite parallel planes. Now there are some assumptions for this analysis of this infinite parallel planes. So what are those assumptions? So the configuration factor or the shape factor of either surface, it is unity. Then there is non-absorbing medium such as air in between the surfaces. And the emissive and reflective properties, these are constant over all the surfaces. So these are the three different points that we take into assumption in case of radiant heat exchange between two non-black parallel surfaces which are infinite. So in this earlier diagram, we can see that the surface or plane 1, it emits the radiant energy, the total emissive power E1, which strikes the surface or the plane 2. Now, in this surface or the plane 2, a part of the total radiant energy, that is alpha 2 E1, it will be absorbed by the surface 2. And the rest of the radiant energy, that is 1 minus alpha 2 multiplied by E1, it is the remainder, it is now reflected back to the surface 1. So now of this remainder, that is 1 minus alpha 2 into E1, again a part, it will be absorbed by the surface. Now that part, it is alpha 1 multiplied by 1 minus alpha 2 into E1. So which can be seen in the plane 1. So this part will be again absorbed by the plane 1, and the remainder, it will be reflected to the plane 2. So that remainder, it is now 1 minus alpha 1 multiplied by 1 minus alpha 2 into E1, which is written above the arrow line in between these two plane parallel surfaces. Now of this remainder, again one part will be absorbed by the plane 2. So that radiant emissive power part, which is absorbed by the plane 2, it now can be represented as alpha 2 multiplied by 1 minus alpha 1 into 1 minus alpha 2 into E1. So in this way we can write the total amount of energy which is actually being reflected from each of these planes. Now we can form one equation that the amount of energy that has left surface 1 per unit time. So if we represent that as Q1, then the Q1, it will be E1 minus alpha 1 into 1 minus alpha 2 into E1 plus alpha 1 into 1 minus alpha 1 into 1 minus alpha 2 square into E1 and so on. So in this way we can formulate the equation for the amount of energy which has left the surface 1 per unit time. Now if we rearrange this equation, then we will get one representation that is in the form of the infinite series, that is actually expansion of the infinite series, which is coming as 1 plus z square plus dot dot dot, where z equals to 1 minus alpha 1 multiplied by 1 plus 1 minus alpha 2. Now this expression, that is 1 plus z square up to dot dot so on, so this is actually the expression of the infinite series, which is 1 by 1 minus z. Now if it is so, in that case we can represent q1, this is equals to e1 minus alpha 1 into 1 minus alpha 2 into e1 divided by 1 minus z. Now after that, if we take this e1 common, then the representation of this q1, it becomes like this. Now as per the Kirchhoff's law that we have discussed while discussing the introduction to radiation heat transfer, in that case we have seen that the emissivity and absorptivity of a surface, these are equal when they experience the same temperature. So in that case, alpha 1, that is absorptivity, this is equals to emissivity for surface 1 and alpha 2 equals to epsilon 2, that is for surface 2. Now you can represent the alpha by this emissivity. So in that case the mathematical representation, it becomes like this. So that means instead of alpha absorptivity we have put the emissivity by using the Kirchhoff's law. Now after 2 or 3 different steps, and if we do the calculation, then we will get one form of Q1, that is E1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. That is our equation number 12.18. So this is actually the amount of equation for the amount of energy that has left the surface 1 per unit time. Now similarly, in case of the surface 2, it is seen that the radiant energy epsilon 2, it will be now go back to the surface 1. So in that case a part alpha 1 epsilon alpha 1 E2, it is absorbed by the surface 1 and the remainder it is reflected back to surface 2. So if we continue in this way, and if we do the calculation that we have done for the surface 1 to evaluate the formula of the Q1, that is the total amount of energy, if we do this similar process for the surface 2, in that case we can determine that the amount of radiant energy which leaves the surface 2 per unit time, it can be represented as E2 epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. So this is the equation number 12.91, which is the amount of radiant energy that leaves the surface 2 per unit time. Now what will be the net flow of energy from surface 1 to surface 2 per unit time? Now to determine the net flow for this two infinite parallel planes, so in that case the net flow, it will be the Q1 minus Q2. So it is Q12, this is actually Q1 minus Q2. Now as we have calculated the formula for Q1 and Q2 in equation number 12.18 and 12.19, so in that case we need to just put their formula here, and after that we are getting the final equation for the net flow of energy from surface 1 to surface 2. This is actually coming as E1 epsilon 2 minus E2 epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. So that is our equation number 12.20. Now here we are dealing with the non-black surfaces. So for non-black surfaces, if we use the Stephen-Boltzmann law, so in that case we will get the emissive power E1 equals to epsilon 1 sigma T1 to the power 4, where we are using the concept of emissivity, and we are also using the Stephen-Boltzmann law. So if we use the concept of emissivity and Stephen-Boltzmann law, then we can write the total emissive power for non-black surfaces, that is E1, this is equals to epsilon 1 sigma T1 to the power 4, that is for the surface 1 or plane 1 as per our consideration, and for epsilon for plane 2 the total emissive power, that is E2, this is equals to epsilon 2 sigma T2 to the power 4. Now if we put this value of E1 and E2 in the earlier equation, that is 12.20, in that case we are getting the equation Q12, this is equals to F12 sigma T1 to the power 4 minus T2 to the power 4 as equation number 12.21. Now what is this F12? This is actually the formula, which is epsilon 1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2, which is actually 1 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is the equation or the formula for the interchange factor from the radiation from surface 1 to surface 2. Now this formula of the interchange factor, that is small f12, for heat exchange between non-black bodies considering two infinite parallel planes. This formula for the interchange factor for this special case, that is for infinite parallel planes, we need to remember to solve the numericals. So this is the way we can derive the equation of the interchange factor and the net flow of energy from surface 1 to surface 2 per unit time in case of the infinite parallel planes, which are non-black bodies. Now let us discuss the heat flow in case of the infinite long concentric cylinder. So till now we have discussed the heat energy exchange for infinite parallel planes. Let us now discuss that heat energy exchange in case of the infinite long concentric cylinder. Now, so this is the diagram that you can see here. So infinite long concentric cylinders have been considered here. So two infinite long concentric cylinders we have considered, which are having areas A1 and A2. Their corresponding emissivities are epsilon 1 and epsilon 2, and the surfaces, these are maintained at temperatures T1 and T2. Now if we use the reciprocity theorem for the shape factor, then we can write that A1 F12 this is equals to A2 F21. So this reciprocity relation we have discussed in the last lecture. So is the formula for the reciprocity relation A1 F12 equals to A2 F21. But in this case F12 this is equals to 1. So what is the reason? Because all the radiation emitted by the inner cylinder, these are intercepted by the outer cylinder completely. So in that case the F12 this will be equals to 1. Now if we put this formula of F12 equals to 1 in the reciprocity relation, so in that case we can write that F21 this is equals to A1 by A2. So this value of the shape factor for F21 we have now calculated, this is equals to A1 by A2. Now let us consider the energy emitted per unit area by the inner cylinder. So the inner cylinder, it emits the energy that is capital E1 as per our consideration. Then the outer cylinder, it absorbs the energy that is alpha 2 into E1. It will be multiplied by the absorptivity. That means some fraction of the total irradiation that which is absorbed by the outer cylinder. So this is equals to alpha 2 E1. So as per Kirchhoff's law, as absorptivity equals to emissivity, so in that case alpha 2 E1 this can be represented as epsilon 2 E1. Now after absorbing some of the irradiation, the remainder which will be reflected by the outer cylinder or the cylinder 2, this is equals to E1 minus epsilon 2 E1. So E1, if you take E1 common, E1 into 1 minus epsilon 2. Now this reflected energy by the outer cylinder, it will be again some fraction of this will be again absorbed by the inner cylinder. So the inner cylinder absorbs the energy. That equation it can be represented as E1 1 minus alpha 2 multiplied by F21 alpha 1. Again, the remainder of this will be reflected by the inner cylinder. So ultimately that remainder part we can represent it mathematically as E1 1 minus epsilon 2 whole multiplied by 1 minus epsilon 1 A1 by A2. Now this absorption and reflection in between the inner and outer cylinder, this will continue indefinitely. So in that case, we can calculate the net energy lost by the inner cylinder if we consider the infinite times absorption and reflection in between these two infinite long concentric cylinders. Now, if we calculate the heat lost by the inner cylinder per unit area, so what will be the heat lost by the inner cylinder per unit area? So this will be based on the absorbed and reflected terms that we have just now discussed in between these two concentric cylinders. Now if we write this equation for the heat loss by the inner cylinder per unit area, then we can represent like this, which we can see here in this presentation. So after two or three different steps, we can write the final step, or we will get this one E1 multiplied by 1 minus A1 by A2 multiplied by epsilon 1 1 minus epsilon 2 whole divided by 1 minus epsilon 2 into 1 minus A1 by A2 epsilon 1. So this can be simplified by the representation 12.22. So this is actually the heat loss by the inner cylinder per unit area. In this similar manner, we can also formulate the equation for heat lost or energy lost by the outer cylinder per unit area, and this can be represented by this equation number 12.23. Now we have calculated the heat lost by the inner and outer cylinder respectively per unit area as Q1 and Q2. So now if we want to find the net radiation heat transfer between the inner and outer concentric cylinder, so in that case Q12 it will be Q1 minus Q2. So now from the equation number 12.22 and 12.23, if we put the representation of Q1 and Q2 here in this equation, so in that case after some steps we will be getting the final term of the Q12 in this way. Now as we are considering the non-black bodies here, so in that case for the non-black bodies, if we consider the concept of the emissivity and Stephen Boltzmann law, so in that case we can write the emitted energy by surface cylinder 1 E1, this is equals to epsilon 1 sigma T1 to the power 4, and E2, this is equals to epsilon 2 sigma T2 to the power 4. Now if we put this value of E1 and E2 in the earlier equation for Q12, so in that case after some steps we will be getting the representation of Q12 for non-black bodies. This is equals to F12 A1 sigma T1 to the power 4 minus T2 to the power 4 as equation number 12.24a. Now this F12, as per our earlier discussion, we have seen that it is the interchange factor or equivalent emissivity between the two infinitely long concentric cylinders. So in the earlier case it was the interchange factor for two infinite parallel planes. So that equation we have seen Now here the equation of this interchange factor, it gets changed because here we are dealing with the infinite long concentric cylinders. So this equation, it is also applicable for concentric spheres, except that for concentric cylinders of equal length. So this equation for the interchange factor, we need to again remember to solve the numericals. Till now we have got two different formulas of the interchange factor in case of the parallel planes, infinite parallel planes and infinite concentric cylinders. So in case of the concentric sphere and concentric cylinder, if they are having equal length, so in that case the ratio of the area, it is represented here. 1 by a2, this is equals to r1 by r2 in case of concentric sphere. a1 by a2, this is equals to r1 square by r2 square. Now let us discuss the small gray bodies. What will be the net radiant heat exchange between the small gray bodies? So let us consider two small gray bodies. Now what is this gray body? So this concept of the gray body, it is already discussed. Now these gray bodies are said to be small if their size is very small as compared to the distance between them. Now here if we consider two small gray bodies 1 and 2, which are having emissivities epsilon 1 and epsilon 2, or absorptivities alpha 1 alpha 2. Now the radiant energy emitted by body 1, the radiant energy emitted by the body 1 is partly absorbed by body 2. Now the portion of radiation which is unabsorbed and thus reflected on the first incidence is considered to be lost in space due to surfaces being small. So that means if it is lost in the space, that means nothing will be returned back to the surface 1. And this similar case, it will happen for the surface 2 also. Now the energy emitted by body 1, that is the small gray body 1, it is a1 sigma 1, a1 epsilon 1 sigma t1 to the power 4. Now the energy incident on body 2, this will be f12 a1 epsilon 1 sigma t1 to the power 4. So in this similar manner, the energy absorbed by body 2 we can also write. Now what will be the energy transfer from body 1 to body 2? So here if we consider the Kirchhoff's law, then you can write the representation of the energy transfer from body 1 to body 2 as Q equals to epsilon 1 epsilon 2 a1 f12 sigma t1 to the power 4, considering the Kirchhoff's law. So similarly, the energy transfer from body 2 to body 1 now, it can be represented as Q2, this is equals to epsilon 1 epsilon 2 a2 f21 sigma t2 to the power 4. And what will be the net radiant heat exchange between these two small gray bodies? So Q12, it will be Q1 minus Q2. So this equation for Q1 and Q2 we have already written, or we have formulated. Now if we use the reciprocity relation or reciprocity theorem here, A1 F12 equals to A2 F21. So in that case, the representation of net radiant heat exchange between the two small gray bodies, it can be represented like this: F12, small f12, A1 capital F12 multiplied by T1 to the power 4 minus T2 to the power 4, which is equation number 12.25. Now this F12, whose formula is epsilon 1 epsilon 2 here in case of the small gray bodies, it represents the equivalent emissivity or interchange factor for radiant heat exchange between two small gray bodies. So the third equation for the interchange factor, which is applicable for small gray bodies we have seen just now. So let us discuss the next derivation, which is the small gray body in case of the large enclosure. Now, let us consider a small body which is placed in a large enclosure. Now that large gray enclosure, it will act like a black body which absorbing practically all the radiation or all the incident radiation upon it and reflecting negligibly small energy back to the small gray body. So in this case F12 equals to 1 because all the radiations emitted by the small body, it will be intercepted by the outer larger gray enclosure. Now if this is the case here for a small body in a large enclosure, so in that case due to the properties the F12, this will be equals to 1. Now the energy emitted by the small body 1 and which is absorbed by the large outer surface or large outer enclosure 2, this is equals to A1 epsilon 1 sigma T1 to the power 4. Now the energy emitted by the enclosure 2, this is equals to A2 epsilon 2 sigma T2 to the power 4. So in this similar manner you can write the representation of energy incident upon the small body 1 and energy absorbed by the small body 1, considering the Kirchhoff's law where absorptivity this is equals to this is equals to emissivity. Now the net energy heat exchange between the small body 1 and the outer large enclosure 2, this is Q12, this is equals to Q1 minus Q2. Now if T1 equals to T2 and Q12 is equals to 0, so in that case we will be having A1 equals to A2 epsilon 2 F21, and for that Q12 this will be equals to as F12 A1 sigma T1 to the power 4 minus T2 to the power 4, that is represented as 12.26. Now this formula of the interchange factor or equivalent emissivity in case of a small body in a large enclosure, this is equals to epsilon 1. Now the net radiation heat exchange between the two gray surfaces, considering both the interchange factor F12 and geometric factor capital F12. So that means if we consider for two gray surfaces both the interchange factor small f12 and the geometric factor based on the shape factor analysis, that is f12, so in that case the q net, it can be represented by this equation 12.27, which is small f12 multiplied by capital F12 multiplied by sigma a1 whole multiplied by t1 to the power 4 minus t2 to the power 4. So this is the equation considering both the interchange factor and geometric factor. Till now, the derivations that we have discussed, for all those derivations, the value of the geometric factor and the interchange factor, it is represented in the below table. So here you can see 5 different configurations are here, and for each and every configuration, the value of the geometric factor, that is capital F12, and the value of the interchange factor, that is small f12, these two values for all these 5 different cases are represented in this table. So for the first case, in case of the infinite parallel planes, the geometric factor capital F12, this is equals to 1, and the interchange factor small f12, this is equals to 1 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Now for the second case, when it is of infinitely long concentric cylinders or concentric spheres, so in that case the geometric factor capital F12 this is equals to 1, and the interchange factor equation we are getting as 1 by epsilon 1 plus a1 by a2 multiplied by 1 by epsilon 2 minus a1. So now for the third case, when the body 1 it is small and it is enclosed by the body 2. So in that case the value of geometric factor capital F12 this is equals to 1, and the value of the interchange factor small f12 this is equals to epsilon 1. Now for the fourth case, when the body 1 it is large and it is enclosed by body 2. So in that case the geometric factor f12 this is equals to 1, and the interchange factor it is equals to 1 by epsilon 1 plus a1 by a2 multiplied by 1 by epsilon 2 minus 1. In the last case, when the two rectangles with common side at right angles to each other, so the geometric factor this is equals to 1, and the interchange factor here this is equals to epsilon 1 multiplied by epsilon 2. So this table for the 5 different configurations, whether it is infinite parallel planes or infinite long concentric cylinder or sphere, then whether it is for small body which may be enclosed by the another body, or it may be two rectangles with common sides. So for all these 5 different configurations, the value of their geometric factor that is capital F12 and the formula for their interchange factor that is small f12. This thing we need to remember to solve the numericals. So this table is very much important in this heat exchange between non-black bodies of this radiation module. So today we have discussed the heat exchange between the non-black bodies. So in the earlier lecture we have actually discussed the heat exchange between the black body surfaces, where we have seen the concept of the shape factor, and the in case of the heat exchange between the black body surfaces we have seen a relation that is known as the reciprocity relation or reciprocity theorem. Now there we have seen the different shape factor algebra and some prominent features of the shape factor, and we have seen the summation rule, then principle of conservation, and different other rules regarding the shape factor. Then based on these different equations and the concept of the shape factor, we have discussed different numericals. So for those different shapes, it may be triangle or hemisphere or a rectangle. So for all those different, or maybe a cylinder, so for all those different geometrical shapes, we have calculated the value of their shape factors. So for that we have used the reciprocity relation and the different formula regarding the shape factor algebra. Now today's lecture we have discussed mainly the radiation heat exchange between the non-black surfaces. So here we have discussed the equation for the radiant heat exchange between the five different configuration. So first one was the infinite parallel planes, and there we have seen a formula for the interchange factor. which is here in this table. Then for the infinite long concentric cylinder or concentric sphere, here also we have got another representation of the interchange factor. Then when the for small gray bodies, when the body 1 it is enclosed by body 2, and again the body 1 large it is enclosed by the body 2. So for all these small gray bodies we have seen the interchange factor representation. And lastly, the two rectangles with common side at right angles to each other. So for this 5 different configuration, the formula for the geometric factor and the interchange factor and the derivation we have discussed today. So this is the end for today's lecture, and in the next lecture we will continue from here. In some numericals we will solve based on this formula of the interchange factor and the net radiant heat exchange formula, and one electrical network analogy for thermal radiation system it is there. So all these things we will discuss in the next lecture. So this is the end for this lecture.